How's it going, everyone? So right now we're moving on to specific heat capacity. There are quite a lot of questions coming from specific heat capacity, and you guys need to be pretty all right with calculating specific heat capacity or change in the temperature or the mass or energy. So firstly, what is specific heat capacity? It is the amount of energy required to raise the temperature of 1 kilogram of a substance by 1 degree Celsius. So the formula for that is E equals mc delta T. Delta stands for change in temperature. E is the energy, M is the mass, C is the specific capacity, and delta T is the change in temperature. So this is the formula we're going to use in this lesson and throughout all these past exam questions which I'm going to solve. Let's get started. So I'm going to take that off from now. And let's go through question number 1. The espresso machine shown in figure 15 is an electrical appliance. The espresso machine has an electrical heater connected to a 440 volts main supply. So that's the voltage. The power of the electric heater is 3.5 kilowatts. So this is the power. The rating of the fuse is the current about which it melts. Which of these is most suitable fuse for espresso machine in circuit? So this question is not about specific heat capacity, but it is followed by a massive specific heat capacity question, and therefore I just put in the part 1 for it, for the context for you guys to get where it is coming from. So firstly, we need to find the current. So in terms of electricity, there is a formula: power equals VI. Voltage times the current is equal to power. So in this case, we're going to make I the subject, so power divided by voltage, and power is 3.5 times 10 to the power of 3. Why is that? Because we have kilowatts, right? We need to convert into normal watts divided by 440. Put that into your calculator and let's see what you're getting. So for me, 3.5 times 10 to the power of 3, which is just multiplying it with 1,000 anyway, 440, giving me a value of 7.95 amps. But we don't have 7.95 amps in the option. So the maximum you can go for is C. So we can go up to 10 amps, and after 10 amps, if there is more current drawn by the wire, the fuse will melt. Okay, so that's how you solve this particular question for 1 mark. Moving on to the next part. Before the espresso machine can be used, its heater must raise the temperature of some cold water. So basically, cold water is drawn into the heater, it's heated up. The specific heat capacity of water is given. So this is our C. C is the letter representing specific heat capacity. Show that it takes the heater about 90 seconds to raise the temperature of 1 kilogram of water. So that's our mass, from 18 degrees to 95 degrees. So we need to show that it takes about 90 seconds, which means we need to find out time, right? And I'm going to take you through, it's a 3-mark question. I'm going to take you through how you can work this out. Firstly, we need to find out the amount of energy that is required to raise the temperature from 18 to 95. How do I know that? Hold on, you will understand why I'm looking for energy. Because we are given with specific heat capacity, we're given with the mass, we're given with change in temperature. You need to calculate the energy required to do that. So energy equals mc delta T. Energy equals the mass is 1 times 4,200 times the change in the temperature is 95 minus 18. And if you put that value in the calculator, so that will be 4,200 times, you can put 95 minus 18. That is going to give me 323,400 joules. This is the amount of energy that is required to do the job. Okay, but we have the power calculated before. What was the power in the previous question? You see, so sometimes be aware that these questions are connected, and that's the reason why I put the first part in this question as well. So here we have 3.5 kilowatts right? So the power here is given to us 3.5 times 10 to the power of 3 watts. Now, power equals energy divided by time. That formula, you need to know that formula. And from this, we can work out the time. So time equals energy divided by power. So energy, we already worked it out. That's here. 323,400 divided by the power, which is 3.5 times 10 to the power of 3. I would like you guys to put that in a calculator. So you can just type that into the calculator and we are getting an answer 92.4 seconds. There we go. So the value of the time, not temperature, the time we worked out is 92.4 seconds. And there we go. That's how we solve this. By the way, an equation from the formula sheet could be used. I just didn't use the formula sheet. It's just, I know the formula, guys, so you can refer back to the equation as well. So that's how you do this one. Okay, let's look at this question, guys. The temperature of coffee decreases as the device is used. So this is about a coffee machine, and the initial temperature of the coffee was that. So the temperature of the coffee is decreasing. The internal energy of the coffee decreased by 15 kilojoules. Density of coffee is given. Volume of coffee is given. Do you know what? When density and volume is given, they're indirectly giving you to work out the mass. So density equals mass over volume, and therefore mass equals density times volume, right? So you can work out mass from there. I'm just going to work out that right now. So the density is 1.1 times 10 to the power of 3 times the volume is 1.9 times 10 to the power of minus 4. Put that in your calculator and you have got the mass in kilograms. All right, so 1.1 times 10 to the power of 3 times 1.9 times 10 to the power of minus 4 is giving me an answer of 0.209 kilogram. All right, so we got the mass of the coffee. Now, specific heat capacity of coffee is that much. Calculate the final temperature of the coffee. So you see, whenever we have change in temperature, we can write T2 minus T1. T2 is the final, T1 is the initial. So is it okay? We say this is the initial T1 and the final we want to work out is T2. Okay, so the formula goes energy equals mass times specific heat capacity times change in temperature, which is our delta T. So we could write the energy here. The energy is 15 kilojoules. So I'm going to write 15 times 10 to the power of 3. Kilo means 10 to the power of 3, okay? And times mass, we just worked it out, 0.209 times specific heat capacity of coffee, 4,200, which is already given. So in this case, we need to be careful. You see the change in temperature. It's usually T2 minus T1. But in this case, you can see the coffee is decreasing. The temperature of the coffee decreases, right? So we want to make sure it is losing the temperature. So therefore, we could write over here 76 minus T2, all right? Because 76 was the initial temperature, and from that, we're losing some energy, correct? There we go. So here, what are we going to do then? So if I take 15 times 10 to the power of 3, and I'm going to divide that by 0.209 times 4,200 is equal to 76 minus T2, okay? So what will happen over here is we have to put this in your calculator. Once you put this in your calculator, you're getting 17.08 equals 76 minus T2. Take 76 to the other side and we're going to subtract it. So that will give us T2, the value of T2, if you work it out, to be 58.91. Okay, so the final temperature of the coffee after it is losing some energy is 58.91. Remember, we are losing the energy, therefore the final temperature must be lower than the initial temperature. So that's how we solve this question, guys. So here's a question about a condenser. Now, if you guys don't know what a condenser is, it changes state from gas to liquid. It condenses gas to liquid. So vapor to liquid is the purpose of a condenser. So the condenser energy transfers energy from coolant to the air in the building. when the total energy input to the heat pump system is that, so that's the energy, you see, the temperature of the air in the building increases from that to that. Now, here's the thing. Maybe you have no idea about what a condenser is. You don't know how it works. You don't have the technical knowledge on it, but that's okay. Read the question. You're given with energy, you're given with two temperature, which is a change in temperature. It says the air inside the building increases from 11.6 to 21.1 degrees. The efficiency of the heat pump is given 87.5%, which is that is a useful energy from there. And here it says total energy input. This is the total here, right? And from that, only 87.5% energy is used. Mass of air is given. That's the mass. Calculate the specific heat capacity, right? So firstly, because you want to work out the specific heat capacity, E equals mc delta T. We know this formula. This is where it all began, right? Now it's a 6-mark question, so it's not going to be that easy. So we're going to do one thing. We got to work out what? We got to work out, you see, the change in the temperature is caused by 87.5% of the energy, because that increased the temperature inside the building. The rest of the energy is lost as heat anyway. So what do? The energy we will take as 0.875, which is 87.5% of, means multiplication, 1560 times 10 to the power of 3. Why do I have that 10 to the power of 3? Because it is kilojoules. So 87%. So we have taken 87.5% of the total energy. Make sense? That's the useful energy is equal to mass is 125 times specific heat capacity. I have no idea what it is. We are working it out. Times the temperature change, which is 22.1 minus 11.6. There we go. This is the full expanded formula here. Now you just make C the subject. So C is equal to, if I make this C the subject, that will be 0.875 times 1560 times 10 to the power of 3 all over 125 times 22.1 minus 11.6. Type that out as it is into your calculator and you work it out. You got 6 marks just for that. So 0.875 times 1560 times 10 to the power of 3. And at the bottom I have 125 times, you need to put a bracket, very important, 22.1 minus 11.6, close a bracket, and I am getting the specific heat capacity to be exactly 1040. Write that value here, 1040, 6 marks with you. So here is another question, guys. The initial temperature of the mixture, I don't know what mixture is picked up from the past exam paper, but it is a mixture, was that the mixture froze at minus 1.5 degrees. So there is a change of state. The total of 165 kilojoules of internal energy was transferred from the mixture to cool and freeze it. So if you want to freeze something, let's say I want to freeze this, I have to take out energy from it, right? So if you want to freeze, let's say, a glass of water, a bottle of water, you put it in the freezer. What do the freezer do? It cools it down by taking out energy from that system, correct? So we have taken out 165 kilojoules of internal energy. Internal energy is simply thermal energy, the sum of kinetic and elastic potential energy of a system. So we have taken that amount of energy out of the system. So the specific heat capacity of the mixture is given, the latent heat of fusion of the mixture is given, and calculate the mass of the mixture in this case. So quickly, to give you a better idea, I'm going to show you the energy. So this is the temperature and this is the energy. Let's say this is 0 degrees, and if we were heating water, let's say we have ice. You would heat ice and then it would not, you will have a straight line here. So it is, let's say it's at minus 10 degrees, and you will reach to 0 degrees, and then you're heating further from there, right? Something like that. So do you see this section here? This is where ice melted. All right. So now what we are happening. So over here, ice was solid. And then from this point to that point, it was melting. And from here, the temperature of ice changed into water. And now it is water. And the temperature of water increased over here. So right now, when we are talking about the mixture being condensed, we're going reverse. So firstly, we're going from there to there. You see, the temperature decrease. It was cooling down. And when there is a change in temperature, we go for specific heat capacity because there's a change in temperature. So what is the formula for that? Energy equals mc delta T. Let's see. So we don't know the mass for it, okay? So the energy taken out, I don't know the amount of energy that was taken out, so I'm just going to write that down. This is the energy taken out while the mixture was cooling down. And the mass, I don't know. That's what we are figuring out. The specific heat capacity of the mixture is given to us 3,500 times change in the temperature. And look, it says it was at 20 degrees, but it froze not at 0, because we don't know the mixture if it's a water or anything. It froze at minus 1.5. So the change in the temperature would be 20 degrees minus of minus 1.5, which would make minus of minus means plus. And that makes it 21.5. Okay, so this is the amount of energy needed to cool it down from 20 degrees all the way until that freezing point, the amount of energy taken out. Now, not just that, plus we got to cool it down further. So at this stage, it is still liquid. Now we have to freeze it to change of state. So we need to take even further energy from it. And that's why we're given with specific latent heat of fusion. And the formula for that is E equals ml. And do I know m? I have no idea what m is. So E equals m times L is given 255,500 right there. That amount of energy. So the total energy, what is the total energy? It's given to you guys here, which is 165 kilojoules. So I'm writing 10 to the power of 3 must equal to addition of that, which is the energy taken out to cool it down from 20 to minus 1.5. So we have m times 3,500 times 21.5 plus, you see, we got to add m times 255,000. So this is cooling down, this is cooling down, and this is change of state. All right, this is E equals mc delta T, and this is E equals ml. All right, so we have to consider when you have to change of state, first it needs to cool down and then change state, correct? So we have both energy coming together. From this, we got to work out m. What I will do, I will factorize the m. So I'm just going to make this a bit smaller. Now we are going to factorize m here. So 165 times 10 to the power of 3 equals m is out. And 3,500 times 21.5, it's giving me 75250 plus. All right, guys, so when you multiply it, it will be exactly the same thing. I'm just factorizing m from it. Then we have 255,000. So the value of m equals 165 times 10 to the power of 3 divided by the addition of that value. So that will be 330,250. Put that in your calculator and you got your answer. So 165 times 10 to the power of 3 divided by 330,250. And that is going to give us mass equal to 0.499. But it says to two significant figures, so that'll be 0.499. 50 rounded. So it's a half kilogram required. 6 mark calculation question. Thanks for watching. So let's see how this is done, guys. A scientist cooled the air inside a container. The temperature of the air went from 20 degrees to 0 degrees. Now, you might be familiar with heating. Cooling is exactly the same thing. We're just reversing the process. The formula stays exactly the same, all right? The volume of the container stayed the same. Explain how motion of air molecules caused the pressure in the container to change as the temperature decreased. So this is not to deal with specific heat capacity, but I would like to, it's connected with that. So here you see the temperature of the air went down from 20 degrees to 0 degrees. The volume of the container stayed the same. So what should happen in that case? If the temperature goes down and the volume stays the same, then pressure will decrease. Okay, but what do we mean by volume? Let me give you a context. Let's say the container was a cylinder just like that. So it was initially 20 degrees. So when it is at that temperature, all the molecules inside that container is moving quite fast, correct? At 20 degrees. But when you cool it down, you're taking energy away from all the molecules. So the molecules are going to move slower, and therefore it will cause a decrease in pressure. So you want to make sure, explain how the molecule, so the question is, explain how the motion of air molecules cause the pressure in the container to change as the temperature decrease. So you would write the pressure decreased. All right, you want to make sure the pressure decreased. Why? Because the molecules have less kinetic energy, right? They have less kinetic energy. Or you could also, it says allow less speed or velocity. And how does a pressure decrease? Because of that, fewer, or you could say so fewer collisions. All right, the word collision is quite important. With the walls, with what? Less force and fewer collision with walls of the container. So this will answer you. Explain how the motion of the air molecules cause the pressure in the container to change. So you've mentioned the pressure would decrease. It's not just changing. You're specifying, saying that pressure will decrease. The molecules will have less kinetic energy, so there will be fewer collisions with the walls of the container, and you got 3 marks for that. So that's how you would answer it. You can always put this in your own words. So moving to the next part of the question, the air contained water that froze at 0 degrees. The change in internal energy of the water as it froze was that the specific latent heat of fusion of water is given here. Calculate the mass. So this is quite easy. E equals ml. All right, the energy is given. Energy is 0.70 kilo, so that is 10 to the power of 3. And mass, I don't know. And the latent heat is 330 times 10 to the power of 3 as well. So m equals 0.70 times 10 to the power of 3 divided by 330 times 10 to the power of 3, and put that in your calculator. So that would be 0.70 divided by 330. That's it. So 0.70 divided by 330 is giving me a value of 2.12 times 10 to the power of minus 3. That is the mass of ice. I believe that is just, you could even write it as 0.0021, or you could write it in standard form. Not a problem with that. So that gave you another 3 marks. So here is another question, guys. Let's have a quick look. The power of the kettle is given. The kettle took that amount of time to heat 0.8 kilogram of water from that temperature to 100 degrees. Calculate the specific heat capacity to two significant figures. 6 marks. Nice question. E equals mc delta T. But we don't have E. So instead of E, we have power. power equals energy divided by time. So we're given with 2.6 times 10 to the power of 3, because it's in kilowatts, is equal to energy divided by time, which is 120. Cross multiply that, that is our energy. So the energy is 120 times 2.6 times 10 to the power of 3, giving me an answer of 312,000. That's our energy. So the energy is 312,000 equals mass. Mass is given, of course, 0.80 times specific heat capacity of water. I don't know. That's what we are working out. Times the change in temperature simply is 100 minus 18, which is 82. And now we're just making C the subject. C equals 312,000 divided by 0.80 times 82, and the value of C can be worked out there. 312,000 divided by 0.80 times 82 is giving me a value of 4756.09. Now, you see over here, it is asking you to round your answer to two significant figures. So what you're going to look at, you look at the first two digit and look at the third one. It is 5, so it's more than 4. So we would round the previous digit by add one more to it. So this will be 4,800 joules per kilogram degree Celsius. That is how you will answer this 6-mark calculation question. So here is another electric kettle. Mass is given. Of water is 25 degrees. The kettle is switched on. After a while, it reaches 100 degrees. Specific heat capacity is given. Calculate the amount of thermal energy supplied by the kettle to the water. Give it an appropriate number of significant figures. Use the equation from the equation sheet. So E equals mc delta T. You must be very familiar with this formula now. Energy, we don't know what it is. We are working it out. Mass is 1.41 times 4,200 times change in temperature is 100 minus 25, which is 75. Put that in your calculator. 1.41 times 4200 times 75 is giving me 444,150. And of course, energy supplied, you could round it to two significant figures. So that would be 44, and we will replace with 3 zeros in here. And there we go. That's how you do that. Guys, just to make sure, even if you write down 3 significant figure, you will still get the same marks. Not a problem with that. So to the second part of the question, the kettle is kept switched on and the water continues to boil. So they did not switch it off. After a while, the mass of water in the kettle decreased to that. The thermal energy supplied to the water during this time is that. Calculate the specific latent heat. So of course, the specific latent heat equals ml, right? And mass here is the amount of water which changed the state, and therefore we got to go back to the previous mass. So initial mass, so mass initially was 1.41. All right, that was a mass right there. Do you see that? 1.41. And mass finally is 1.21, which means the difference between it was converted into steam, change of state. So it's asking you to work out the latent heat and the energy supplied during that time while the mass converted is given. So 450,000 is equal to the mass, which I would write 1.41 minus 1.21, that times L. And if you work the value of L, so if you work this out, this is going to be 2250,000. Okay, you could round it to whatever, but the exact answer here is acceptable and you will get full marks for this. So this is 2250,000, and there you go. That's how you do this question, guys. So this is a slightly longer question, guys. So I'm going to go through it really quick. A student wants to determine the specific heat capacity of copper. Figure 2 shows a piece of copper with a thread tied around it in a glass beaker of boiling water. So the copper will absorb quite a lot of energy. The copper will get hot because we're We put it in boiling water right there. The student leaves the piece of copper in the boiling water, so the copper reaches a temperature of 100 degrees. So the student left it for a while, and the copper temperature is 100 degrees. The student used the thread to take the piece of copper out of the boiling water. The student put the a piece of hot water into a different beaker of cold water. So from there to there, cold water at 20 degrees. Okay, the apparatus is shown. The student assumes the thermal energy gained by the water here. You see the cold water will become a little bit hot because it gained some energy from the copper, right? That equals the thermal energy lost by the piece of copper. So when you took this piece of copper from there to there, let's say the piece of copper was at 100 degrees, which it was. When you put it into cold water, the temperature of the copper will drop and temperature of the water will rise, and they will be at equilibrium. Okay, so what's happening? The copper is losing the energy to this cold water here, correct? So the student is assuming it is the same energy, that the amount of energy lost by the copper is equal to amount of energy gained by the cold water. The water and the copper both reaches 22 degrees. So from 20 degrees to 22 degrees, cold water gains that amount of energy, mass of the copper is given. Okay, now calculate the value or specific heat capacity of the copper using these results. Okay, so of course the formula is given to us. We are given the cold water is gaining that amount of energy. So that is 1050, that is the amount of energy. And the mass of copper is given 0.058 times specific heat capacity. So, and the change in the temperature of the copper was at 100, now it is at 22. So 100 minus 22, which is 78. And if you make C the subject here, C equals to 1050 divided by 0.058 times 78. Put that in your calculator and you will get your answer. 0.058 times 78 is giving me a value of 232.09. There we go. So you could round this to 230 if you wish to. That is the specific heat capacity of copper from this. So it does says accept 232 as well. So you could write it that way, or 230 if you want to round it to significant figures. So the value of heat capacity of copper obtained from students' result is lower than the correct value. State two ways the experiment could be improved to give a value that is closer to the correct value. So you see in that we want to make sure the amount of energy that is lost by the copper is gained by the water, correct? So we can include, these are all the information. There are quite a lot of ideas. Reduce heat loss from water by using insulated beakers. So you see this beaker here, this one here, we could use an insulated beaker. We could also use a stirrer to make sure the energy is efficiently transferred throughout the water. We could also argue transferring the copper from there to there quickly. It needs to be quick, otherwise copper is going to lose energy to the surroundings. Use a different heating method, possibly, not just water. You could use a different heating method, perhaps. So any of those two arguments which will improve the results, especially using an insulation, would give 2 marks for you in that case. So moving on to this question here. A beaker contains 0.25 kilogram of water at room temperature, and the beaker of water is heated until it reaches boiling point, and specific heat capacity is given. The total amount of thermal energy supplied to the water is that. Calculate the temperature of the water before it was heated, which is what is the room temperature. So E equals mc delta T. Energy is 84,000 joules, and mass is 0.25 times specific heat capacity is 4,200 times change in temperature. So it's 100 minus T1. You see that? 100 minus initial temperature. So these two values, which we will multiply and divide by 84,000. So 0.25 times 4,200 gives me 1050. So we have So we will have 84,000 divided by 1050 equals 100 minus T1. And so 84,000 divided by 1050 is 80. 80 equals 100 minus T1. If I make T1 the subject, 80 goes here. T1 equals 100 minus 80. T1 equals 20 degrees Celsius. And that gave you 3 marks for that calculation. The heating continues until 0.115 kilogram of water was turned into steam. The thermal energy needed to do that was that much. Calculate the specific latent heat. It's even easier. 2 marks. E equals ml. And energy is 0.34 times megajoules, means 10 to the power of 6, equals mass is 0.15 times L, which is the latent heat. So L equals 0.34 times 10 to the power of 6 divided by 0.15. Put that in your calculator. 0.34 times 10 to the power of 6 divided by 0.15, and that is giving me specific latent heat. Again, you look at the unit, guys, it is megajoules. So the answer for L I'm getting is 2266666.6. So I want to convert into megajoules. I'm going to take 246. So it's going to be there, and I'm going to round it to 2.3. So this is 2.3 megajoules per kilogram, and there you go.